All right, we are at the end of Unit 5. Salt hydrolysis is definitely the least fun part of this unit, though. These problems are just long, so there's lots of room for error. It's nothing crazy new or anything. Well, some of it's new at the beginning, but the rice table stuff feels very the same. Um, so here's what our final pH thoughts are going to be based on. They're based on the idea of what if instead of a solution is made with acid that you can analyze as an acid or base that you can analyze as a base, what if it's just salt that's dumped in? What's the definition of the word salt in this class? Ionic, any ionic compound. A metal with a non-metal, boom, salt. Table salt is NaCl, which a lot of y'all think about when I say salt. So we could use that as one of 1,000 examples. So here's what I'm asking. If I were to take this red water, and start dumping table salt in it, would the pH go up or down or not change? And different salts do different things. And that's what today is. Can we judge a salty solution, not necessarily clearly acidic or basic solution, and find its pH? In order for us to do that, there's some foundational stuff that we have to understand about the origin of salts. Do you remember that a neutralization reaction is when an acid reacts with a base to form salt and water? It turns out that salt is born from acid-base reactions, which is why it's so ingrained in what we're studying in this unit. So with that said, I want to investigate a salt with you. Let's look at sodium chloride. As I mentioned a moment ago, what if you took table salt that's sitting in any restaurant's table and you just started dumping it in the water? Does it change the pH of the water? And if it does, which direction? Well, here's what your job is. Your job is to find the parents of the salt and examine their strengths. Now, what do I mean when I say the parents of the salt? Well, since salt is born from acids and bases interacting with each other, I know that whoever made that little baby there, one of the parents started with an H, while the other one ended with OH. Mom and dad, right? They went to prom together. They had one of those nights. NaCl, there it is. All right, nobody wanted him. Here he is. Has been born from these parents. So if you look at the ions that create these dudes, well, it turns out that sodium is Na plus, chlorine is Cl minus, and you can easily attach these items to mom and dad. How do I know we can easily do that? Well, because hydrogen over here has a positive potential, while hydroxide has that negative potential. So I can figure out who these pieces originally belong to. The positive would have been attracted to the negative, meaning one of the parents is sodium hydroxide. Do you see how I got there? Yes. The other ion would have been negative, which would have been attracted to this dude, meaning the other parent is hydrochloric acid. I have found mom and dad. Now I just need to know their strengths. Luckily, you do, because you've already been tested on it in Unit 2. HCl, strong or weak? Strong, because it's binary. I bring clay. NaOH, strong or weak? Strong, because that is a group 1 hydroxide. Strong. And what happens if the parents are strong? The pH doesn't change. So you just solved the dinner mystery. If you go and you sit at a restaurant and you start dumping salt into the water, the pH of the water does not change. But let's do a different salt. Let's do calcium carbonate. Here's the formula for calcium carbonate. All right, he's +2, -2, so there's no crisscross. All right. You know how I know he's salty? Is because a polyatomic is bonding. If a polyatomic bonds to anything, it's ionic. If you have an ionic compound, it's salt. I want to know, what's the pH if you dump calcium carbonate into solution? Well, again, the moment we start asking about salts, I know that I'm looking for mom and dad there. I know that if I split that salt, the calcium would be an ion of +2, while the carbonate would be an ion of -2. If you look at polyatomic info and stuff like that. I know that this hydrogen parent likes to be positive, while this hydroxide likes to be negative. Again, oxidation state data. So here's the association. The positive and the negative are going to attract. So this will be H2CO3, because carbonate would cross his 2 while we're being good little chem kids. Yeah. That negative would attract that positive, making him calcium hydroxide. And there is dad and mama. Let's draw a card. Let's go over to cluster 2, seat 5. Hey, 2-5. What's the strength of H2CO3? I mean, it's either strong or weak. Maybe you'll impress everybody. Guess. Strong. No, it's definitely not. What an answer. Yeah, you know how I know it's weak? Is because that's an acid. Do you agree it's an acid because it starts with H? It contains carbon. Do you agree it contains carbon? Automatically weak then. Also, the HO ratio would make it weak. Let's go over to cluster 5, seat 4. Hey, Aspen, what is the strength of calcium hydroxide? Strong is correct, because calcium hydroxide, there was a weird thing that happened. I skipped 6-4, but it is listed at U13. So anyway, yeah, it's strong because calcium is one of the 3 group 2 hydroxides that are strong. Hooray for our brains. Our question, though, is what's the resulting pH if you drop calcium carbonate into water? Is it going to go above 7 or below 7? Above 7, because we just look over here. All right. If the base is strong but the acid's weak, the pH will go above 7 because it's going to be more basic. Right? If it's got a more basic parent, it'll have more basic implications. You try one. I want you to find the pH consequences of the salt ammonium nitrate. I'll write it out for you if you're feeling slow this morning. Ammonium nitrate. Figure out what happens to the pH if he's dumped into the solution.
we'll have no weak interaction.
All right, let's see how you did. I know that we've got ammonium and nitrate. I know that ammonium's positive is going to go that way, while nitrate's negative will go that way, meaning mom and dad should be nitric acid alongside ammonium hydroxide. I know that the strength of HNO3 is strong because look at the H to O ratio that you do when you are not a binary acid. I know ammonium hydroxide is weak because it is not a group 1 or special group 2 hydroxide, meaning I would expect, since we have a strong acidic parent, for the solution to therefore be more acidic with a pH below 7. Do you see how we're doing this? Okay. That is the first main half of today, is your ability to get the conceptual part of this. These conceptual questions are usually MCQs when they show up in May. The FRQ part of this is when they're not so general, because right now we're saying less than 7. But what about when they want to know the number? Less than 7 is great, but if they want to know the exact value that's less than 7, things get more complicated. In order for me to prepare y'all for figuring out the quantitative part of this, I want to look at a dissociation equation and just remind you of some basic Bronsted-Lowry stuff. So methylamine chloride is what it's got over there, and it wants us to write the dissociation equation for that. So let's do that real quick. CH3NH3Cl. CH3NH3Cl. It wants us to write the dissociation equation for this substance, which means just break it apart, right? Now, where do you break it apart? That's not real easy to see if you're not to the trained eye, but look at the name of it. It needs to break apart into methylamine and chloride, and I know you can see the chloride, which means now you can find the methylamine. So sometimes you have to use that context of stuff that you do know to identify the leftover stuff that you don't know. So this would dissociate into the methylamine. And chloride. Right? So again, the way that I know that those are those products is because I know that chloride is Cl-1 for sure. So then the rest must be the opposite type of ion. So that's just the normal dissociation. Nothing real weird there, but look at the next question. It says it wants us to prove the acidic character of that substance, the CH3NH3+. In order to prove that, we could show it in Bronsted-Lowry because we know how items with acidic character act in those situations. So what I'll do then is take the CH3NH3+, all right, which is exactly, it pulls that out in the question. And we can add it to water to identify its acidic character. Now, it's labeling it as acidic, right? You're not super trained to look at that and know it's acidic even though it is, right? It's actually that plus that makes it acidic. But if it's being referred to as an acid by the question and it's containing carbon, then it must be weak, which is why it would have all of this stuff going on. But regarding Bronsted-Lowry, we know that items with an acidic nature want to do what? They want to get rid of a proton. We want to get rid of an H+. All right, so let's shove one of these H+'s over to my amphoteric water. And you'll end up with CH3 NH2 with no charge, one less H, one less plus. Of course, that moved over to water. And we've proven then the acidic nature of it because it formed hydronia, which is the acidic substance in addition to hydrogen ion. And then it says write the equilibrium expression, which would just be K equals those two over him, not the water, because I'm not going to write it out. I don't want us to, we're on a Thursday for you people at home, so I'm worried about the bell ringing before I do the actual work. But yeah, the K expression would be those two over him. So the reason I'm showing you this, though, is you're about to see how the salty parent stuff we did at the beginning and this idea are going to join together for us to find quantitative properties of salts altering pH. Before we start, though, this next slide might be the most important. Oh my God. Come on. Might be the most important slide in the unit because this slide prepares you better for your exam than any other. This is basically the math of the 3 lectures summarized. In the first lecture, we were only doing negative logs. We did a bunch of other stuff, but math-wise, we were only doing the negative log of strong, because strong samples, negative log gives you pH. In the second lecture, we were doing weak samples, which we didn't get to use that, not at the beginning of them anyway. We had to add it to water in a rice table. And then finally, we have these salts that we're about to really dive deeply into. But realizing on your upcoming exam, am I looking at a strong acid base? Negative log. Am I looking at a weak acid base? Water in a rice table. Am I looking at salt? Then it's what we're about to do, which is, again, slightly different. So that differentiation on your part is really important. By the way, that yellow highlighter that was on that screen is really important. You'll hear me say those words, but you do have them written down already. All right, well, let's have a little bit of fun. We're going to work out 2 problems, hopefully both before the bell rings. Let's start with our first guy here. Calculate the pH of a 0.7 molar sodium acetate solution. Sodium acetate is salt. I know it's salt because there is a polyatomic bonding. All right, acetate's polyatomic. It's over there bonding to a metal. So I know, I'm analyzing the pH of salt. And the first thing you do right away when you realize it's this worst type of road is you find mom and dad. All right, so we are dealing with that salt. All right, oh, no, we're not. Sodium. I don't know where I got the H. That was from the Ka. Sorry, we're dealing with sodium acetate. I know one of the parents is going to be the sodium with hydroxide, while the other parent will be hydrogen with acetate. Now, if it's strong, then you don't have to do anything because the pH is going to be 7. You already know the answer. But if one of them is weak, then that item does what we call hydrolysis. If they're both weak, you're in the wrong class because that's beyond our scope. It won't happen in here. So, which one is weak? One of them is weak. Which one is it? Yeah, this one right here. That is a weak acid. All right, this is a strong base because that is a carbon-containing acid, yeah? Here's what you do. The strong parent will be a spectator ion. It's not going to do anything, so you will ignore him. The weak parent is going to have an effect on pH. All right, we know that the pH is going to be above 7, right? We've already drawn those conclusions. If we have a strong base, the pH will be above 7 at the end of our work. We'll prove that true. But what we need to know is how the weak sample is going to affect that number above 7. All right, so he's picking the range, and he'll pick where in that range it is. The way that you're going to do that is we are going to do, what's called hydrolysis of the weak parent, which includes adding the weak ions to a rice. So listen to my words again. You're going to take the weak ion, all right, which is this dude here. It's the acetate ion. And we're going to add it to water in our rice table. All right, so our ion here is actually the conjugate base of this parent. So we know that he's acting basic automatically based on on lecture 1 skills from this unit. And bases want to gain a proton. So let's give him a proton. Transfer the H plus over. Now, here's an absolute. If there's any part of you that's sitting there and you're like, wait, why did you do that? How did you know to do that? I'll keep explaining it. But here's some good news, is that this substance that you make over here will be the parent that you had discovered earlier, if that helps you at all. I don't want to confuse you more. But a way to check your work is when you start hydrolysis, your R row should create the parent that you found when analyzing who you were going to hydrolyze in the first place. No, it doesn't matter. I. You mean you did the water plus that? Oh, or you did the hydroxide first? Yeah, that doesn't matter. It's not going to match my work. And then of course, when that H plus transferred over, it left him as hydroxide. Right, and now this really starts to rhyme with a lot of stuff that we've already done. Initial concentration, we have that. It's 0.7. All right, and none of these guys to start. Do our shift. Reactants down. Products up. I plus C equals E. All right, we are looking for pH, and we have Ka. And here's where hydrolysis is really annoying. Look here. We're given Ka because this parent here is what we're basing our rice table off of. But we need the opposite species because we're building a basic environment. This always happens when you're analyzing salt, where the K value they give you is the wrong one. They gave us Ka. We need Kb, but it's a very easy fix. And this isn't a moment where you're like, oh, well, I'm not going to know when I need to switch my Ka to Kb. You do right away. If you are doing hydrolysis, if they gave you salt instead of acid or a base, you've got the wrong K for sure. So watch how I fix this right away. It's Kw divided by Ka will give me the Kb that I need. And you've got all of your values there. So I'm going to go 1 E negative 14 is Kw divided by Ka, which is given in the problem, 1.8 E negative 5. And that will spit out a Kb of 5.6 E negative 10. And now the rest is everything that we did in lecture 2. So really the only difference in hydrolysis, though it's annoying, is the first part where you need to figure out who's going to hydrolyze. All right, find the weak dude, the weak ion, and put him in. And then also realize that you're always going to have to do this step. Kw divided by one of them gives you the other one. But now we can plug and chug to do the rest of our work. So let's get our K expression going. Now I have the correct K. All right, remember, we're going to the E row, always to the E row for our K expression. So there's the products is X times X over the reactant, 0.7 minus X. Hey, are we going to do a quadratic? No, we don't want to, though. What are we going to do instead of a quadratic? Trump X. All right? Remember, if minus X is a denominator, we are now allowed to get rid of that. And now the math is much simpler, right? So we can imagine this over 1. 1 times X squared would be X squared. 5.6 e negative 10 times 0.7. We'll have to find that value. See if you like that green number that I found. Isolate the X. Square root. And then don't forget what you have found. Why is that useful? Because X is actually a hydroxide concentration. Now that is super useful because I know that if I go negative log of a hydroxide concentration, it gives me POH. So we can go negative log of 1.98 e negative 5. Which will give me a POH. I get 4.703. This question wants pH, though. And we know that pH plus POH equals 14 for a final answer of 9.297. And I know this is long and difficult and complex, but don't give up on me. Yeah? Hey, look, we proved it though. Look, the pH is above 7 just like we knew it would be because we had a strong base dad. Hey, we've got 10 minutes. Think we can do another one? Oh, look at them. They all done it. Yes. Excitement. They weren't mean to me just there. Let's go one more. We don't have time to draw any cards, so just absorb, but do ask questions. You're welcome to stop me. You're more important than all these stupid people at home. Stupid. Here's our last problem of the day. Right, let's do this. KClO. KClO. That's an ionic compound. One of the parents is KOH. Another parent is HClO. As I find their strengths, I know that we have a strong base and a weak acid because of the H to O ratio. That makes him weak. The strong parent is a spectator. We don't do anything with him. The weak parent is going to have effect on the pH. Remember, the strong, again, it's going to be above 7 because we have a strong base. But this is going to decide where above the 7 we go. And so we're going to hydrolyze the weak ion, which is not the H. It's just going to be the ClO minus in our rice table. So I'm going to take that weak ion. The weak ion is ClO minus, and add them to water in a rice table. And I know that that first step is going to create the parent that I had found. We can prove it with Bronsted-Lowry, right? Because this is a conjugate base. So the base is going to accept a proton. So you can think about that however you want. But there's that proton donation. We ignore the liquid water. The initial concentration given is 0.355. And we have none of this data. We are really good at our shifts. And I plus C equals E. Any questions right here? Don't suffer in silence. I love to explain myself. All right. The sprinkle that we have is a K value. It usually is for hydrolysis. But what's true about the K value anytime we started off with that parent step? It's the wrong K. All right. So I'm going to take that K, 3.5 E negative 8, and make it a part of my KW thought. I know that 1 E negative 14, which is KW, divided by Ka, 3.5 E negative 8, will equal Kb, or Kw divided by Kb equals Ka. They all talk to each other like that. Dun, dun, dun. .9 E negative 7. What did y'all get for? You got 2.9. Oh, 2.9. Yeah, 2.9. Yeah, E negative 7. Yeah, that number's okay. Why aren't we taking what? That is two sig figs. Two.
We took 3 in
Oh.
because there were 2 in the E last.
Yeah, but at this point, I was still at 2. 1.0, 1.8, and 5.6. No, you're good. I'd rather you ask than sit there and think I'm crazy. All right, now we have a good K, and now the rest, now there's no tricks, unless you think that stuff we do in here is always tricky. But anyway, we've got a KB, so now we can plug and chug. So let's go K equals products over reactants, right? So we'll go 2.9 E negative 7, that's K equals the products from the E row are X and X. The reactants from the E row is 0.355 minus X. Worst announcement of the week. Let's keep solving and finding X. All right, so let's do our cross dots here, and we'll have X squared equals. Remember, trump that. We trump that negative X. I'm sorry, people at home. This is probably the most annoying video right now, but can't do anything about that voice. Multiply that diagonal. (1.03 e negative 7). Isolate the X, square root. The square root of that X value to get X, sorry, of X squared, 3.21 e negative 4 molar. And then track what you found, right? This part's so easy. We've got X, find the X and realize that it does give you good information. And we're actually in a identical situation than what we were in last time on the problem. All right, we now have a strong sample because you can see that if you take the negative log of hydroxide, that it just flat out gives you POH. So we can go negative log of 3.21 e negative 4, which will give me a POH. 3.493. It doesn't round up to 9.4. 3.493. You got 90 seconds. I'm killing it. And then, of course, pH plus POH is 14. For a final answer of 10.507. And you'll notice that this one is more basic than the last one, right? If you compare that pH. So those two salts that we just analyzed, while both of them had strong basic parents, so they were both made that pH rise. One of those salts was more basic than the other, right? Based on that resulting pH. Round of applause if you hate this. They love me.